So what we did last time was looked at forces on submerged flat surfaces. Now we're going to extend it to submerged curved surfaces. Okay, so the main confusion on these problems is the weight. Okay, it has to do with the weight of the fluid. We are going to use the weight of the fluid in order to figure out these problems, or the weight of some fluid in order to figure out these problems. But you got to remember, it's not the weight of the fluid that's causing the forces on these submerged surfaces. It's the pressure that's causing these forces. And the pressure is due to depth, right? It's not due to the actual weight of the fluid. It's due to depth. Okay, so let's look at an example. What we have here are 3 containers, different shapes, all right, and all have the same fluid depth. All right. If you look at it, remembering that force is due to pressure, pressure is due to depth, they all have the same depth. Therefore, all those F's of the water acting on that surface is the same. Doesn't look like it should be the same because they have different amounts of fluid in them. Therefore, they each weigh a different amount, right? That's called the hydrostatic paradox, okay? And this is because the pressure at the bottom is the same, and pressure is rho GH or gamma H. And since P is constant over the surface, because you're not changing the depth over this surface, that means you can just say, well, force equals pressure times area, because pressure is equal to force divided by area. And in this case, it's gamma HA. All the same in all 3 cases. Okay, so let's think about these 3. For the middle case, that's the easiest one. F does equal the weight of the fluid, so that bottom surface is actually holding up whatever fluid is in there. Okay, makes sense. On the right, let's look at the right because that's the next easiest. Okay, what's going on is there is a pressure over here, right, due to that fluid, and it's going to act perpendicular to that surface. All right, and it is going to have a net downward force, okay, but the sides are going to counteract that. Okay, so there's always the equal and opposite force going on from the vessel to the fluid. Okay, so that is going to help hold up some of that weight. Okay, this is from vessel on fluid. So I guess that does make sense, right? The weirdest one is on the left. Okay. On the left, your pressure force is going this way, right? Kind of up, perpendicular and towards the surface, which means the vessel, this wall, is actually pushing down because it's equal and opposite for this case. Right? So it's pushing down and that's contributing. So you not only have the weight of the fluid, but you also have the walls pushing it down and increasing the total force of the fluid that acts on that wall, on that bottom wall. All right? Weird, right? But all that works out because pressure forces are due to depth, not due to the actual weight of the fluid. P is due to depth. Now, of course, the weight of the fluid comes into it because if you had a heavier fluid, you would have a bigger F than if you have a lighter fluid. In all 3 cases, though, they would be the same. All right. So to solve these, we are actually going to use weight, and I guess that's where part of the confusion comes in. But what we want to do in all these problems, the first step is to draw an area here, or a volume. We want to draw a volume, and that volume we want to draw always goes straight up from the sides of the surface to some known pressure. In this case, it's where we have P atmosphere acting. Okay, and key, always draw these lines straight up. Okay, no matter what the shape of your container is, the lines are going to always go straight up. Okay, so in this case, we are going to be talking about the fluid, the weight of the fluid above the surface, because it just so happens when you draw it straight up, that is above our surface, the fluid above the surface. Okay, so in order to come up with the equations that we need to solve this, what we're going to do is divide this into parts, and for our curved surface problems, we're going to solve the vertical component of the force separately from the horizontal component of the force. Okay, and we're going to be able to figure out what these equations are by just doing a free body diagram on that fluid that we just drew, fluid above the surface. Okay, so if we do a free body diagram on the fluid, we're going to have the fluid weights, we're going to have a force due to air on that fluid. The fluid pressure is going to push this way, and therefore to keep this static, we're going to need forces pushing back towards the fluid at all of these surfaces. When we get to our curved surface down here, we're going to end up with both a vertical and a horizontal component of our resultant force, F4. So let's analyze this, and what we want to do is separate out the horizontal and the vertical. Okay, so let's do the x direction, and what we've done here is block this out so we get a nice easy shape here on the top, and then we get the part that has to do with the surface here. So if we look at just the top block, if this is a statics problem, some of the forces in the x direction have to equal 0, and what that tells us on this top block, the only x forces are F1 and F2, so F1 has to equal F2. So now let's do the x direction with both blocks. Still a statics problem. So our x direction forces are F1 plus, that's an F3, minus F2 minus F4H. Okay, so again, we're dividing this into the horizontal and vertical components of the F4. That's the one we're really looking for, is F4. That's the force on the submerged curved surface. All right, well, from this, F1 equals F2, that means we can cancel those. And what we find is F4H is just equal to F3. Okay? And that is what we're going to use to find the horizontal force. So F3 is something we can find. We already know how to find the force on a flat plate. So let's pretend that this is a flat plate. Okay? And if we pretend that that is a flat plate that has the same shape as the straight up line that you drew and extends from the lowermost point of that surface up to the shallowest point of that surface, that is like a horizontal plate or a vertical plate that you know how to solve. Okay, that's where you do your YCP and your force equals P at the center of gravity times area, right? So you can solve that. So your horizontal force, F4H, is equal to the horizontal force on a vertical projection of your curved surface. All right, so that's what we're going to use in order to find our horizontal force. So now let's look at the vertical force. Again, statics problem, some of the forces in the y direction have to equal 0. So if we just sum up all of these, we're going to have our F4V going up, and then everything else going down, W1, W2, and F air. And those have to sum to 0. Okay, so our F4V, our vertical component, has to equal W1 plus W2 plus the force due to the air here. And the force due to the air, that is going to be equal to P, in this case, P atmosphere times that area of the top, whatever that is. Okay. So basically, this is the weight of the fluid above it, and then plus any component if you have to take P atmosphere into account. Okay. So we can say the vertical force in the curve is equal to the weight of the fluid column above. So I say fluid column above because there may or may not be fluid in that column. It doesn't matter what the shape of the container is. You got to draw your line straight up from the sides. Okay. This straight up line that you're drawing as well is going to help you figure out what is the shape of that vertical projection, okay, that you're going to use like a flat plate analysis on. Okay, so you got to think about that column of water above the surface. What is its shape? And then just extend your flat surface from the deepest up to the shallowest part. And that is going to help you find the horizontal projection. Okay, also, just like before, if we have P atmosphere acting here, and let's say this problem, you would also have P atmosphere over here, which would act around to the bottom of the surface, and they would cancel out, and then you could get rid of that F air part as well. Okay? And then it would be the weight of the fluid above. So let's look at that with respect to these three containers again with different shapes. I don't know what all this is. Anyways. So just we know that the force is due to pressure, and that's equal to gamma times H times A, right? So we could also use our curved surface method. So let's look at the vertical component, and the vertical component on this is going to be the weight of the fluid above. But remember, this is the part to remember, always draw your fluid above as if it's going straight up from the bottom. So in this case, you would draw up to here, like that. That's what you would use to find the weight of the fluid above. In this case, it'd be the actual fluid. In this case, it wouldn't be all the fluid. It'd be straight up. So draw your line straight up. That's going to be key. All right, so the vertical component is the weight of the fluid above. And how do you find weight? Given specific weight, well, that's going to equal gamma times the volume, right, of the shaded part I have in there. So it's not necessarily of the actual fluid, it's what you get when you draw straight up. So again, always draw your volume straight up, and you'll be doing well from the surface. Okay, to figure out the vertical projection to use for the FH part, what you're going to do is use the portion of the side of the volume, so it would be like the sides, these sides, just the portion that extends from the deepest part of the surface up to the shallowest. So on our old surface here, our deepest part of this surface was here, and the shallowest was here. So that's what we would use for our vertical projection. It'd be a flat plate, and if that was coming straight out of the page, that would be a rectangle. For this one, however, the deepest part is equal to the shallowest part. They're at the same level, the whole thing, so FH is going to end up being 0. The whole surface is at the same depth. Okay, and that makes sense. So go ahead and stop and do questions 1 through 3, and then we'll continue with one more video.